Yeah, welcome everyone from Budapest. I hope you find it nice in Bordeaux. So I'm afraid I can't offer, well, neither wine nor cheese, but what I can offer is a talk by Carla, who I think is one of the most promising young commentators I know. So she just defended her PhD in Oxford and she's now doing a postdoc in the Netherlands. And I'm looking forward to her talk. Carla, please.
Yeah, thank you very much. And it's a great honor to speak at such an historic event. So this talk should not require much prerequisite knowledge about universal graphs and labeling schemes. So I'll explain those later. And it's about two joint works of the past year, which we did on Big Blue Button during the pandemic. So I thought at that time it was sort of round Europe. So you can see my co-authors here, Alex Scott, Marthe Bonamy, Cyril Gavoy, and Louis Espret. So let's start off with what a universal graph is. So in my case, I'm looking at induced universal graphs. And this is a graph. This contains all graphs from a certain graph class as an induced subgraph. So we could consider, for example, the 3 vertex graphs, and then we can wonder how small of a graph can we make that contains all these graphs as induced subgraphs. Well, we need to contain a triangle, so let's just put down a triangle. And we need to contain an independent set of size 3. So let's just add that as well. And now one of the graphs we already have. And there's one last one that we need to contain. So let's put down one more edge. And now the graph depicted on the left-hand side contains all the graphs on the right-hand side as induced subgraph. Okay, so this was for 3 vertex graphs. What about 4 vertex graphs, 5 vertex graphs, etc.? Can we always make one? Well, if we think a little bit about it, there's one obvious way to make it. For example, on the right-hand side, we also have one. So we can just take the disjoint union of all graphs on n vertices. So this has the number of n vertex graphs times n vertices. And how many is that? Well, about 2 to the n squared. So you can see some kind of precise asymptotic at the bottom here. But this is about 2 to the n squared over 2 vertices. And now we can wonder, can we do much better than this? And one way to obtain such induced universal graph is through a labeling scheme. So I'll give the formal definition of this later, but that's a bit of a mouthful. So let's again start off with an example. So we're given some kind of graph and we want to assign labels to all the vertices so that if you get any pair of labels, we know whether there's an edge between the corresponding vertices. So here I've already labeled my vertices with 0 up to 4. The labeling scheme doesn't know the original graph. So one obvious thing we could do is we can just write down their names and also write down all their neighbors. So here vertex 0 is adjacent to vertex 1 and vertex 3, etc. And in the definition, we actually want to get a bit string, but that's quite easy to do. So we need log n bits for the name. And then we use n bits to just write down for each vertex whether it's adjacent to it. So 0 is not adjacent to 0, but it is adjacent to 1 and 3. So let's check that this indeed works. If we now get the first label and the second label, then we can read off the names. And then we can decide to maybe look in this sequence, look at this position, because we know that encodes adjacency to the vertex named 1. And we can see whether there's an edge or not. So how much smaller can we make such bit strings? Does anyone see anything that we can improve in this scheme? There's a bit of redundancy here in that both 0 and 1 have encoded the adjacency between 0 and 1. So we can actually get rid of that. And instead we can put our points on a circle and only record the adjacencies to the next n over 2 vertices on the circle. So in this case, the vertex with name 0, it records its adjacencies to the vertices with names 1 and 2. And the adjacencies to 0 are recorded by vertices -1 and -2. So now instead of log n plus n bits, we only need log n plus n over 2 bits, which is quite a lot better. And in fact, it will turn out that actually this is almost tight. up to this log n factor, this is sort of the right answer. Okay. So why did we want these labeling schemes again? Well, we wanted to construct these induced universal graphs. But it turns out these notions are actually sort of equivalent. So if we consider the labels in an adjacency labeling scheme, then we can create an induced universal graph by having as vertex set the set of labels. So if we have labels of size fn, then there's 2 to the fn possible bit strings. So we have 2 to the fn possible vertices. And you can check that actually this correspondence will give this claim that in a adjacency labeling scheme with labels of size fn, you can make an induced universal graph with 2 to the fn vertices and vice versa. So I've got a little drawing of this as well. So this is if we look at the labeling scheme of moon from before. What are the possible labels? Well, we have 3 possible names, 0, 1, and 2. And then we only have to record one adjacency just to the next vertex. And there's always 2 options. Either you're adjacent to your next vertex or not. And you can now also check by hand that the graph that's constructed here contains all 3 vertex graphs as an induced subgraph. Okay, so let's now look at the more formal definition of such an adjacency labeling scheme. But this is a little bit of a mouthful. So in the end, it's about you're getting 2 labels, which are just 2 bit strings. And then we want to give a decision whether the 2 vertices are adjacent or not. So we want to assign each n vertex graph in some kind of graph class a label of length fn, so that we can decode from the labels whether the 2 vertices were adjacent or not. And we say that the labeling scheme has labels of size fn exactly if these labels that we decide that we assign are length fn. And there's one more technical assumption that I've put down here, which is that distinct vertices must receive distinct labels. So this already puts some lower bounds on the size of our labels, because we know that each vertex needs to get a different name. So the labels need to have size at least log n. There's another lower bound that we can obtain via counting. So we can also look at the collection of n vertex graphs in the graph class. And this will also give us a lower bound on how large the labels need to be. It's kind of intuitive, like if there's more graph, you need more labels. So if we obtain a sequence of labels, and let's assume that all of our graphs are on vertex set 1 up to n, then we can actually completely reconstruct a labeled graph. And therefore, the number of n vertex graphs is upper bounded by the number of sequences of labels. So we have n labels, there were 2 to the fn possible labels. And if we rearrange this, we get the following lower bounds on any adjacency labeling scheme in terms of the size of the graph class. And this is already very interesting for the class of all labeled graphs. We have n choose 2 possible edges, so there's 2 to the power n choose 2 possible labeled graphs. And if we now fill in this bound, well, we take the log and then we cross out this n. We see that we need at least n minus 1 over 2 bits to encode any adjacency labeling scheme for the class of all n vertex graphs. And remember that before we saw that we can do it in n over 2 plus about log n bits. So this was actually in some sense tight. So actually you can prove a very tight result about this, which Noga Alon has done. You don't need the extra log n term. So in our work, we were interested in what other situations this counting lower bound is tight. So in fact, this won't be true for all graph classes. And one thing that you can notice is that if you can adjacency label a certain graph, you can also do it for all its induced subgraphs. And of course, if we add the induced subgraphs to the graph class, then this quantity, this lower bound, only goes up. So it's somewhat natural to assume that we've already added all the induced subgraphs to our graph class, that we've sort of taken the highest possible lower bound. And that's when a graph class is hereditary. So we say it's a graph class hereditary if it's closed under taking induced subgraphs. And for those graph classes, we can show that we can match the lower bounds up to an additive factor of little o of n. Yeah, I think this is a really cool result, but let me mention two limitations of this. So first of all, our little o of n term is not super great because it arises from Szemeredi's regularity lemma. And secondly, it's not always interesting. So of course, this is only interesting if this term here on the left-hand side is actually the leading term. So that won't be the case for things like planar graphs. But for example, for triangle-free graphs and perfect graphs, for those kinds of graph classes, we get a asymptotically tight labeling scheme. Are there any questions so far about our main results and main definitions? Let me also mention here maybe that there is some kind of notion of efficiency that I'll get back to later. And then we can do that as well, but then we have to replace this by delta n for every positive delta. But I'll get back to that later in the talk. Okay, so as I mentioned, we obtain our results using Szemeredi's regularity lemma. And this is a very widely used technical lemma with lots of applications. And this is probably the first application in the labeling scheme community. And it's quite a difficult lemma to state, so I've just drawn a picture to try and explain it. So the lemma, you give it some kind of epsilon, and then it gives you for a certain constant, so that for any graph, even if it has 1 million vertices, you can partition it into at most that many parts. So this constant doesn't depend on the number of vertices. That's very important. So this partition, it actually reduces it to a finite problem for us. We can really store everything that I've drawn here into each label because it will just be a constant. And now what it tells us is some kind of control on the edges between the parts. So there's an epsilon fraction, a small number, which we don't really have control over, but there's not too many of those, so we can shove it into our little o of n term. And then we split it up further into parts of high density and parts of low density. This is quite a standard thing to do. And then we can look at the remaining edges and we can draw the reduced graph, which is depicted on the right here. So I've repeated this picture in the bottom, and what we find in the end is this decomposition of the vertex set for some constant that we just store entirely. So we store this entire thing in each label. And now we have some edges which are incident to V0 and some red edges, but there's only, we can sort of assign about epsilon n for each vertex, well, some function of epsilon times n for each vertex to record these red edges. And also if we know that the degrees are the density is very low, we can somehow convert this into low degrees and again store a small number of adjacencies per vertex. So I'll explain later how we're going to do that, but we can use some kind of techniques to reduce it to this problem here. And now the leading term that we'll get, that will actually come from the reduced graph. So each hereditary graph, we have some kind of graph theoretic results are known about them. And for example, if the graph is triangle free, then this reduced graph doesn't have any triangles. And then of course, by Mantel's theorem, it has at most n squared over 4 edges. And that will actually precisely correspond to the leading term in our labels. So I just wanted to mention a little bit more about this step now, about how we actually encode these adjacencies. So the idea is that each vertex encodes some kind of small subset of size epsilon n. And the sort of most obvious way to do it is to just write down all the elements, but that would take too many bits because we would need log n bits for each element times the size of S, but the size of S is epsilon n. So then we would need n log n bits, and we only want to do in something like n bits, a quarter n bits, for example. But actually, information theoretically, we wouldn't need as many bits as we are doing here. But what you can do is you can take the log of the number of things you want to encode, and information theoretically, that's sort of the lower bound for the number of bits that you would need. So in this case, there's n choose epsilon n subsets of size epsilon n. And if we take the log of that, then we can upper bound it by some kind of function which tends to 0 as epsilon tends to 0, which is the binary entropy function. But the important bit is that this part is this can really become part of our little o of n term. If we can indeed encode this close to the information theoretic minimal. So for this, we use a bunch of existing results called King dictionaries. And they allow you to encode a family of subsets with a label size which is near the information theoretic minimum. And there's one other property that it gives us, and that's fast membership queries. So this is all in some kind of computational model, which is called the word REM model, where we're not allowed to inspect k log n bits, but we are allowed to see k words, where each word takes log n bits. But this is a slightly technical difference between these. And what we were actually originally interested in is getting efficient labeling schemes, for which the encoding takes polynomial time, and we just can look at a constant number of words in order to see whether two vertices are adjacent. So this makes a lot of sense if you would actually want to apply this, that if you actually assign labels, it is very nice if you only have to look at a very small number of bits in your label in order to see if the information that you're trying to decode. So this is quite a strong assumption, but in the end, we're helped a lot by these existing data structures. And they managed to do this for us, basically, for this part of our proof. So they can really, in a constant number of words, you can see if an element is part of a set or not. So there's a few more details that I've sort of left behind, but this is sort of the rough idea of how our construction goes. So let me mention a few corollaries of our results. So the thing that we were originally interested in is reachability in directed graphs. So for reachability, we're given two vertices, and we want to know is there some directed path from U to V or not. And the best known bounds were n over 3 plus little o of n with an efficient scheme. And we wanted to improve this to the lower bound of n over 4. And our main result immediately implies this, because we can consider comparability graphs, which is a hereditary graph class. And there was a known way to sort of to reduce adjacency labeling in comparability graphs. You can reduce that to comparability in posets, and that again to reachability in digraphs. So those optimal labeling schemes we all get for free from our main result. But for these settings, we also have an alternative second proof, which just uses a lot of very clever combinatorial ideas, and it doesn't use Szemeredi's regularity lemma at all, which allows us to do a little bit better, because remember that this remember that this little o of n term was really horrible. So we can actually replace this by something more of the form like 1,000 times some polynomial in n. If we want to get it efficient, we can also do that while still not having a horrible error term. So of course, another corollary of our main result is that we also get asymptotically optimal induced universal graphs. So yeah, just from the correspondence I stated before, we get this number of vertices. But yeah, one quite interesting open question here, I think, is that it would be interesting to also maybe ensure that this induced universal graph is actually part of the hereditary graph class that we started out from. And one case that's in particular interesting are universal posets, because we get comparability labeling schemes on n over 4 bits. So we get a universal poset on 2 to the n squared over 4. Well, that's just by taking disjoint unions. And we get a universal graph for the set of comparability graphs on this size. But this doesn't have to be a comparability graph itself, because this adjacency labeling scheme doesn't really allow us to control that much about the universal graph itself. And that also brings me to the second part of this talk, where we're going to try to get more properties on this universal graph than just being induced universal. And we'll see that it's actually quite difficult to find a good labeling scheme that really gives this correspondence, because here we have this very nice correspondence between adjacency labeling and induced universal graphs. But we haven't been able to find this for the isometric universal graphs. So here I've got a little picture to show you what an isometric subgraph is. So it's always an induced subgraph, but now we also want the metrics to coincide. So for example, on the left-hand side, it's not an isometric subgraph because the vertex, the leftmost and the rightmost vertex in the bigger graph, they're distance 2, whereas in the subgraph, there's distance 3. Whereas on the right-hand side, it is an isometric subgraph because the distances are all the same. So now we can define an isometric universal graph for a graph class to just be a graph that contains all graphs as from this graph class as isometric subgraph. And we can ask again, how small can we make it? Well, first question is, of course, does it exist? So it's quite easy to see that it always exists because we can still just take disjoint unions of n vertex graphs. And then we have about 2 to the n squared of them. And yeah, a question asked by Peter Winkler is whether we can actually do quite a bit better than that. So he proposed to study these objects and whether we can get improve this quadratic in the exponent to a linear bound. So the way that the induced universal graphs were constructed, there's sort of 2 ways which I've seen. First of them is taking random graphs, and the second are via labeling schemes. So random graphs are going to be a bit difficult because they tend to have small diameter, and therefore they can only contain graphs of small diameter as isometric subgraphs. So a natural question is then, can we do it via some notion of labeling scheme? So we haven't been able to find something precisely equivalent, but we have found sort of 2 related labeling schemes. One of them already existed and one of them we've invented that allowed us to answer this question. So the first labeling scheme is a distance labeling scheme. So this is very much like an adjacency labeling scheme, but now we want to assign labels so that from any pair of labels, we can find out the distance between the corresponding vertices. So it turns out that if we have an isometric subgraph, we can turn it into a distance labeling scheme, but the other way around doesn't really work because we don't really have that much control still over the graph that we create. So we've introduced this notion now of a distance vector labeling scheme, which is quite a bit stronger at first sight, because now instead of finding a single distance, we're going to get all the distances, and instead of giving it 2 labels, we'll only give it a single label. So the distance vector labeling scheme, from a single label, it needs to give you the distance of the vertex u to all the other vertices in the graph. And as I alluded to before, these isometric universal graphs, they give you distance labeling scheme, but these distance vector labeling schemes, it turns out that they do give you an isometric universal graph. So in order to construct these, we just have to construct good distance vector labeling schemes. So I think, yeah, this implication is quite easy to see. This one, it's not super difficult, but it takes a bit more thinking, I think. So let me maybe show you a very easy example of a distance vector labeling scheme. Because one thing we can do is, of course, just not do anything. We can just write down the whole list of distances in the label. So this is sort of a case of no compression at all. For each, so I've given an example here below, the vertex 0, it sees that it's a distance 0 to itself, distance 1 to the other vertex, distance 2 to 2, 3 to 3, etc. And these are the distances that 1 has to the other vertices. And these are the labels that we'll assign. And now we're going to put 2 edges in this graph exactly if the infinity distance between these 2 vertices is equal to 1. So in this case, we see the infinity distance equal to 1, so we put an edge. And that's how we're going to construct our isometric universal graph. And now the idea is going to be that we can track in this graph of labels what certain indices are. So each part of the label can only jump by 1 each time we transverse an edge. So in this case, if we first focus on the entry 0, we can only go to points which start with 0 or with 1 if we want to do a step in our big graph. So we know that it needs to take at least 3 steps to reach a position which starts with 3. So maybe this gives you a little bit of an idea how these distance vector labeling schemes will give us isometric universal graphs. And note that how large are my labels now? Well, they're of size n to the n. So what we find is we can get an isometric universal graph on n to the n vertices, which is just a set of labels. So now we have 2 to the n log n, which is not exactly what we wanted. We wanted to get some kind of constant times n. But using some tricks from distance labeling, we can improve this further to the constant log 3. So we can do 3 to the n plus a smaller order term and find an isometric universal graph on that many vertices. So let me finally mention some open problems. So when I started off, we had this question of when can we match the counting lower bound? So we saw that we can match it for graph classes which have about 2 to the n squared vertices elements. So what about if we have 2 to the little o of n squared? So there's an old conjecture about this, which concerns hereditary graph classes with 2 to the order n log n graphs in the graph classes. And the conjecture is that for those you can match basically match the counting lower bound. So note that this log n was necessary for the names, and it's also necessary for the counting lower bound. If this is maybe a theta here, but yeah. So this is I think quite an interesting open problem, but it's probably quite a difficult one because the behavior of these kinds of graph classes is already not super well understood. So also getting an adjacency labeling scheme for them is probably even harder. So yeah, but I think it's an interesting question to see if this is true. And secondly, there's quite a lot of questions related to this new notion of an isometric universal graph. So of course, the most obvious one is what's the best we can do? Can we actually get the same amount as we would get from the counting lower bound for this? Or do we really need some more if we want to have this additional notion of isometry in there? And there's also this new notion of a distance vector labeling that we've introduced. And we haven't been able to really separate this from the normal distance labeling scheme, for example. So I think both upper and lower bounds for the distance vector labeling scheme would be interesting. And already for the distance labeling scheme itself, it's for the class of all graphs, it's not known what the best thing is that you can do. So I think in this direction, there's also quite a lot of things left to be explored. Well, thank you all for your attention.
Thank you very much, Carla. I think we can all unmute ourselves and try to give her a round of applause. Thanks, Carla. Are there any questions for Carla? We have plenty of time, so even if you have a long question or a technical one, go for it.
So for distance vector labeling, if I understand correctly, that's exactly the question, how many different distance vectors from a single vertex you can have in a graph.
Yeah.
Right? And this, so the best known bounds that you know for this?
So yeah, I can maybe tell a little bit more about what we can do with it. So there's sort of one small trick that you can see to get a lot better with, which is quite easy to understand. So suppose that there's some kind of Hamiltonian path in your graph. Well, it's not always the case, but let's assume that there is. Then what we can do is instead of encoding the distances to the vertices, we can also record the differences between the distances. So we have one which we record entirely, and then we have these differences. And these differences are now always in -1, 0, 1, because there's always an edge between the vertices in a row. So the difference between your distance to V1 and V2, it has to differ by at most 1 by the triangle inequality. So now you can do it in about 3 to the n. So what we've managed to do is basically get this 3 to the n to work also for graphs which don't contain a Hamiltonian path.
I see.
Yeah.
Maybe because the cube of the graph always contain a Hamiltonian path? Or?
Yeah, that gives you 5 to the n if you do that.
I see.
But yeah, there's also, so you can, of course, if there's a separator, you only have to record your distance to the separator. Because if both of them know that distance and they know that there's a separator there. So you can do quite a bit better for planar graphs with ideas like this. And what we do in the end is we take some kind of depth first search tree. And then we're going to, then you know that each edge will be to one of your ancestors. So now what you're going to do is you're going to record the names of your ancestors and you're going to record the distances to your ancestors.
I see. And in the lower bound, the best lower bound, you know, for the number of vectors?
Yeah, I'm not sure. I think that's, I mean, there's the counting lower bounds. We have some lower bounds in our paper, but I think it has some additional assumptions, but I would maybe have to ask Louis for
okay.
what this specifically means.
Good answer.
But not a great lower bound.
Okay, thanks.
Yeah, if you really have to record all your distances to all your neighbors, now the natural lower bound is not 2 to the n over 2, but 2 to the n, because you don't have the symmetry that you have in the adjacency labeling scheme or universal graph.
Right. So for a random graph, it would be something like 2 to the n, right? Because they are all. Yeah.
But yeah, exactly. Just a simple counting argument tells you that you lose the symmetry that gives n½ instead of n in the exponent.
So yeah, also the distance in the distance labeling community, they can do log3 over 2 here instead of log3 by combining with Moon's trick again. So we can't do that. So we're sort of a factor 2 away from the best distance labeling bounds because we can't do the Moon argument anymore, basically.
Thanks. Any further questions for Carla?
May I put forward maybe a silly question about universal graphs? Does it make any difference if you only want to find all connected graphs instead of just every graph of vertices? I mean, if you because in a sense that you might say, okay, I'm not so much interested in having graphs of different connected components, so I'm just interested in.
Yeah, so that doesn't really make a big difference because you can always take the disjoint union of n different universal graphs for those, and that actually gets shoved into our error terms in our case.
Okay, so that's already enough for that argument. So it doesn't really matter whether you ask this or that. Okay, good.
Yeah, we actually consider connected graphs because also in the spanning tree argument, I guess it's in the depth first search tree, it's kind of convenient if the graph is connected. But that's a good question.
Yeah, because somehow from my background ages ago, so as fields, I was in connection with some people who do what they call graph labeling, but obviously this is a different community that really look into tons of very specific labeling schemes and ask obviously different questions. But anyways, yeah, okay. And then sometimes they only get connected graphs, something like that, for instance. So, but okay, thanks.
Thanks. Any other questions for Carla?
I was wondering.
Yeah, go ahead.
I was wondering when in the adjacency labeling you don't insist that different vertices have to have different labels. What happens then? And also, does it still have some connections to the universality problem?
So I guess for the universality, it will be annoying because they can be mapped to the same vertex, right? But I mean, I think you could study, of course, again, the label sizes. For the questions that we looked at, it wouldn't really have mattered because this log n, we get it for free, basically. It always goes into a little of n term. But I don't really know if people have studied this, whether you can maybe do much less than log n, whether any results are like that. I haven't seen any results. Maybe Noga knows.
It will not. I don't think it will make a difference because random graphs do not have repeated vertices. So for random graphs, you anyway need to make them two distinct ones. So the lower bound that follows by counting will follow even without assuming it.
But for a specific graph class, which is maybe
size, I'm talking
pretty small one.
The class of all graphs, right?
Yeah.
For specific,
because otherwise we have the other lower bound as well, I guess.
Sure, yeah. For specific, you may need.
Yeah.
Okay, thank you.
Thanks. Any further question?
I have a question, maybe a naive one. Does it have to do with Kolmogorov's theory of information?
Does it have to do with, sorry?
With Kolmogorov's theory of information.
Kolmogorov information theory.
Yeah.
Oh, I wouldn't know that the answer to that question.
Okay.
I'm not very. So Kolmogorov complexity is also about how many bits you need to encode.
This is what I meant. Yes, this is what I meant.
But those are basically also counting lower bounds typically, right? I guess the Kolmogorov complexity of a graph class would be the same as the number of graphs in the graph class, or not? Or like, I don't know, like maybe the log of it or whatever.
I don't know. I think his measure of complexity is more or less the same. The minimal number of data, so to speak, which allows you to specify a given searched for element in a given set.
Yeah. I guess the really interesting thing to me about these adjacency labeling schemes is that you don't just represent the graphs, but you spread them out over the vertices somehow, all the information. And what I think is very interesting is that you can do this without losing information. So basically you don't have to put too much redundancy in the labels. And for example, especially maybe the result of Noga as well, that you can do it for all the class of all graphs exactly tight. You're really not losing any information. You can still distribute it so that locally everyone knows what's going on. I think that's quite cool about it.
Any other question for Carla? So I have a small question, that I can force you to answer in public. So what do you think about this implicit labeling conjecture? Do you think it should be true?
I don't know. Yeah, I could imagine that it's true for all hereditary graph classes that we can match the counting lower bound, in which case this implicit graph conjecture is true. But I've heard people say that it's probably not true, so I don't really dare to say that too strongly. But yeah. I think it would be interesting because I also have a slide about that actually. There's like an example of a graph class which doesn't meet the counting lower bound, but in some extent it's a bit mean because it uses this fact that it's not hereditary by just putting in a smaller problem, like putting in the class of all n vertex graphs into your graph class on n squared vertices. So it's, actually this example is quite easy. So maybe I can explain it so if we say we have the class of graphs average degree 2021, then we just need to select out of the possible edges, we need to select at most 2021 n of them. So we actually don't have too many graphs in our graph class. But of course we can, any n vertex graphs, we can force it to have low average degree by just adding a lot of isolated vertices. So if we add about n squared isolated vertices, then the average degree will drop below 2021. So if we look at the graph class for all the graphs on n squared vertices, then we get the big set of all n vertex graphs as induced subgraphs of these, and therefore we'll need at least n-1/2 labels of size, at least this at that point already. Whereas from this one, we'd expect to need the log of n squared, which is still about log of n. But yeah, I do feel like this is a bit cheating with the hereditary properties. So I think it would be interesting to maybe find one which is hereditary and which doesn't meet the counting lower bounds. So, and I think that that's probably also a much more manageable question than proving the conjecture. I think trying to find a counterexample might be easier. I mean, it's already, I think, already not well understood what these things look like. So yeah, it might be a nice thing, open problem actually, to try to find a counterexample to it, which is hereditary. But I do think that would be interesting to see.
Thanks. Any further questions for Carla? We still have 5 minutes before we get cut off to go to New York. So I have some more questions. But if no one else wants to chat today, it's coffee time. So we have this theorem for dense graph classes, and there's this connector for sparse graph classes. So what happens in between? Can we have similar stuff, or does weirder things happen?
You mean, well, so, yeah, I said this more generally, right? Like I think that it could in general be true that for all graph classes, this counting lower bound is matched. I think also outside of this range, but yeah, I know that there are some graph classes for which this behavior of Gn goes up and down a lot and is very heretic, but it could still be that your optimal adjacency labeling schemes just exactly follow these curves, I think.
What do you mean by erratic behavior?
Well, I've heard that there are some results that it doesn't, like you can't say, oh, it just grows as n to the epsilon or something. Like the growth can sort of change in different regimes of large n. But yeah, I don't know if there's people who've thought that much about this below this range. I don't know what do you think, Marthe?
That's cheating. That's not allowed. So for the new notion of labeling, this vector distance labeling you introduced, do you have any? I mean, you said it's hard to understand like what's going on, but still you could have some intuition of what should happen there. Do you think it's intuitively? Do you think it should? It could be kind of like for adjacency labeling where the lower bound seems so far to always give the good one. I mean, I'm not saying it is true, I'm just saying so far we don't have any reason to think it's not true. Do you think something similar could be true for...
That we get the bound n for distance. Yeah, so that's already a question for distance labeling schemes, whether the normal notion, whether you can reach the n/2 bits, I guess.
For vector, it has better chances of being false.
Maybe, I would say, yeah. But in some sense, the vectors one is also easier because you're looking at a single vertex. I think it's just something that people haven't really studied yet. So maybe there's some, yeah.
There's also an interesting difference between induced universal graphs and this isometric universal graphs. That a random graph G and 1/2, it's a very good induced universal graph if you take it to have the right size. But they are very bad isometric universal graph because the diameter is very small. It's constant, so you cannot contain any graph as isometric graph. So you only contain graphs of diameter at most 3 as isometric graphs. So maybe one of the main differences is that you random like graphs, they're not good examples. You have to do things by hand. Maybe you lose a lot.
Yeah.
Because of that. So if I understand correctly, in the proof of Noga, for the -1/2, you does a random component and a constructive component. But here for isometric things, the random component seems to be a bit useless at the moment.
Yeah, I don't know if the symmetric graphs of Noga's construction would be an isometric. I haven't checked that actually. I guess Noga will know.
You muted, Noga.
Probably not. I think, because they just use labeling schemes, I think. So probably it's not good for distance.
I see, thanks. Any last question for Carla before we start traveling again? So if not, let's maybe try and mute ourselves and then give a second and last round of applause. Thanks, Carla.